So this unit's called Functions and Relations. We talked a little bit about what a relation is last class, and really it was kind of a review because for the most part you guys have seen relations before, right? Some sort of connection between two variables. And so even if you didn't necessarily use that vocabulary, you've certainly worked with them, right? Both in math class and in science class. Anytime you're graphing two different variables, you're working with a relation. Okay. Today we're going to talk about functions, and functions are a very specific type of relation. Okay. Some relations are functions, but not all functions are relations. They have a very specific set of criteria. Okay. So the first thing I want to do is talk about what a function is. Okay. Now, last class, we looked at different representations of relations, and we talked about two different variables that could be x and y. It could be distance and time. It could be lots of different things. And we spoke about the fact that when you're using these different representations, that each variable sort of goes to a specific place, right? And so I talked a little bit about dependent and independent variables. And so, for example, like if you're making a table of values, then this guy, which is the independent variable, always goes on the left. Right? And this is the dependent, always goes on the right. Okay? And that's pretty consistent for all of the different representations where you have something on the left and something on the right. So you could think of an ordered pair, you could think of a mapping diagram. The other one, though, is the graph. Right? And when we're graphing, the independent variable always goes on the horizontal, and the dependent always goes on the vertical. Okay? Now, why is this important? It's important because I'm going to introduce two new words in a second called domain and range. And those two words refer to one of the two variables, essentially. Okay? So what is a function? The other thing that we could talk about is input versus output, right? So if you have a variable x and you're looking at a variable y. We did that thing at the end of Friday's class, where we were looking at graphing something like this, right? So we have this relation y equals negative x plus 4, and we sort of randomly chose some x values, and we plugged them in to this equation, and we got the y value. Okay, so I'm also going to introduce the words input and output. Okay, the input values in this scenario would be the x values because those are the ones that we're inputting or plugging in to the equation. Y equals negative x plus 6. These y values are called the output values. That's what we get after we plug the x or the input value into the equation. Okay, so this is just some new vocabulary, input versus output. Okay, now a function is a specific type of relation in which every unique input value, so like on Friday's example, those would be the x values. Unique. There we go. Only produces one output value. Okay. This is the most basic definition of a function. Every time you input something different, the output is always something different. Okay? You only get one, well, that's not actually true. Every time you put in an input, it will only spit out one output. Okay? Now, I know that this may seem a little bit abstract, but when we go through some examples, you'll see exactly what you need to look for when you're trying to determine whether something is a function or not. Okay? Now, why do we introduce this? Because basically what I'm going to do today, and the feedback that I always get after we talk about functions, is why are we doing this? Like, we're just complicating a relation which we already know how to work with. Okay? And that is partially true, but it becomes very, very, very important as you get more and more advanced in math, because functions actually communicate a dependency. Okay? The output values or the y values, those are dependent on the input values. And so when you talk about functions or function notation, which we're going to talk about towards the end of the class, we are communicating that dependency. We're showing that the output value depends on the input value, on the uniqueness also of the input value. Okay? Now, domain. Domain is a set of values. It's the set of input values that make sense in a particular function. Make sense or are possible in a specific function. Okay? The range is the set of output values that are possible in a specific function. Okay, so I'm going to give you a really simple example. Hopefully it's simple. Let's say the input values are school days in September. Okay, so that would be the input values that are possible there would be all of the school days in September. Those would be specific dates, besides for weekends and PD days. Those are the input values. Okay? The output values would be, let's say, the number of students in this class on any specific day. Okay? So on September 1st, how many students were present that day? On September 2nd, how many students were present that day, etc. I can't remember specifically which days were weekends. I suppose we could look at a calendar and double check. Okay? What would the domain of that function be? The domain is literally a set of dates, and it's all of the dates where there was school in September. That's the set of input values. So in fact, if I go on to D2L, let's see. Well, I'm not going to do that right now. I'm not going to go into D2L, but I've got a calendar in there where I don't have events on the days that are PD days and weekends. Those would be the dates that are the domain of the function. Okay? The range of the function is the set of output values possible. So when you're thinking about the number of students, there are 32 students in this class. Okay? What's the smallest number of students that could attend on any given day? Yeah. Even less than that. 0. You guys could all be sick or something, or maybe, I don't know what you're doing, but you could all be sick, you could all be on vacation, you could all be doing something else. Not that I would suggest that. I hope that you're not sick, but the smallest number of possible students on any given day is 0. What's the largest number of students that are possible on any given day? Yeah, 32, okay? Now, could we have an in-between value? Could we have 2.5 students? No. So what would the range be? It would be all whole numbers from 0 to 32. Those are the possibilities that make sense for this particular function. Does that make sense? Okay. And it is a function because on any one given day, you can't have two outputs. You can't have on the same day like 29 students present and 31 students present. That doesn't make sense. Yeah?
But what if some people leave?
Well, I'm going to say if you're present, you're here for part of the class. That's a good question. If some people leave, I'm just going to say like the number of students on Power School that I mark present. Right? There's a different code for if you leave early, right? You're still here for part of the class, okay? So that is an example of domain and range. We are going to really dive into the weeds on domain and range tomorrow because there is a specific way that we have to communicate domain and range using different types of notation. Depending on the type of function, the way that we express domain and range is slightly different. So we will get into more on that later, but we're just going to do it like quite simply today. Okay? So let's look at an example and we're going to see, is it a relation and what is the domain and range? Okay? This relation is a relation that associates specific shapes with the number of right angles in the shape. Okay? So for example, a right triangle has one right angle. An acute triangle has 0 right angles. So if we actually sort of make this into a table of values, because it's kind of hard to see, and say here's the shape, here's the number of right angles, okay? A right triangle, that's a really bad right triangle, but there we go, has one right angle. An acute triangle. Acute triangle means all angles are less than 90 degrees. That has 0 right angles. Okay? A square. How many right angles does a square have? 4. Yep. And I should actually specifically draw them in. A rectangle. How many right angles does that have? How many right angles in a rectangle? Yep. Also 4. And finally, a regular hexagon. Do you guys know, firstly, what's a hexagon? Yep.
It's a six-sided shape.
Six-sided shape, yes. What's a regular hexagon? What does that mean? Or any regular polygon?
Is it a shape with equal sides on each? Or is it
Little more than that, yep.
equal angles?
Equal sides, all sides are equal, all angles are equal. So actually a square is a regular quadrilateral, okay? So a regular hexagon, all sides are equal, all angles are equal. How many right triangles are in there? Yep, correct. Sorry, how many did you say? None, yes. I thought you said 1. None is correct. Yeah, none of those are right. Okay, all right, so here's sort of, we've transformed this representation from a set of ordered pairs into a table of values. For each input value, is there only one output value? Does a right triangle only have one number of right angles? Yes. Okay? It's not possible to have a right triangle that has 1 or 2 or 0 right angles. It only has 1. Okay? What about an acute triangle? Is it possible to have 0 or 1 or 2 or 3 right angles? No, there's only one possibility. Okay? What about a square? Yeah. Yeah, there's only one possibility for output there. Okay, and rectangle? Could I have a rectangle that has less than 4 right angles? No. Could I have a rectangle that has more than 4 right angles? No. So this is only one output. And similarly, a regular hexagon only has one possibility for number of right triangles. It can only have 0. Okay? What does this mean? This means that this is a function. Okay? This is a function because each input only has one output. So this guy is a function. Each input only has one output. Okay? The domain of this function, a domain is a set. And anytime we refer to a set in math, we use a set of curly brackets. Okay? So when we are trying to communicate what the domain is, we use these curly brackets. So what is the domain of this function? It's all the input values. So the input values are right triangle, acute triangle, square, rectangle, and regular hexagon. And then I'm going to close that bracket off to show this is the set of input values that I could have in this particular function. Okay? The range is the output values. One thing to know about this is, firstly, if a number comes up more than once in the domain or the range, we'd only list it once when we're creating our set. So you could see there's 2 4s, there's 2 0s, there's 1 1. There's only 3 different values. So those are the only ones I'm going to list. And typically when they are numeric, we list them from least to greatest. Okay? So the range is 0, 1, and 4. It's the domain and the range. Okay? Now, one thing that I should note is that it is possible to have the same output value that goes with 2 different input values. That's okay. Right? Just like if you think about on any given day in September, well, if all of you are here on 2 different days, then both of those output values are going to be 32. That's fine. You can have the same range value or output value be associated with different input values, but it cannot be the other way around. You cannot have the same input value associated with 2 different output values. Okay, so sometimes that's confusing for people, but if you practice a little bit and sort of keep that in mind, you're really specifically looking at input and whether there's more than one output. Yeah?
So does that not count for the square because both the 4s are the same values?
Yeah, but these are output. Square only has one output value. Rectangle only has one output value. They happen to be the same value. That's okay. But when you specifically look at an input, it only produces one output. Okay? All right. Now, here's another example. Okay, this is a mapping diagram. We are saying that these input values are the square of these output values. Okay, so for example, 1 is the square of -1 and 1, because -1 squared is 1, 1 squared is 1. 4 is the square of -2 and 2. Right, -2 squared is 4, 2 squared is also 4. 9 is the square of -3. For some reason, 3 is not included in the range, but of the values that are listed in the range, 9 is just the square of -3. Okay? Is this a function? No. Right. How come? Yeah. Yeah. The input of 1 has 2 possibilities. It could either be -1 or 1. Okay, so not a function. And if you are asked why it's good enough to just say there's at least one input, for example, 1, that has 2 outputs. That is justification. There are several input values that have more than one output. Okay? So this is not a function. And by the way, anytime you are looking at a mapping diagram, if there's more than two or more arrows coming out of a value, it's not a function, because that means it's associated with 2 values. If there's more than one arrow going into a value on the output side, that's fine. But you really have to focus just on this part, because again, we're really just looking at inputs and what they're associated with. Okay, we can still list a domain and range here, but it's just not a function. So the domain values would be 1, 4, and 9. And the range values would be -3, -2, -1, 1, 2, and that's it. Yep.
On a test, once you figured out it's not a function, do you still need to list the domain and range?
Depends what I ask, possibly. You don't have to list them unless you're asked to. Yeah. Okay. So I'm going to give you guys a couple of minutes to just look at these examples, figure out if A is a function and if B is a function or not, and also list the domain and range. Thing that I noticed was that a lot of people tried to switch representations to help clarify. That's an excellent strategy. The more we work with these, you'll be able to tell. There's things to look for in every different representation to be able to tell whether it is or not. Okay. This is not a function because there are the input of 6 has 2 different outputs. Okay. One thing that you can look for in either a set of ordered pairs or a table of values is any repeated input values. If there's an input value that comes up more than once, that means that it has 2 different outputs. Okay, so I know a lot of people did like mapping diagrams here, which is great because I already told you what to look for there. You're looking for more than one arrow coming out of a number. When you have either ordered pairs or you have a table of values, look for repeated input values. Okay, so for table of values or ordered pairs, look for repetitions in the input values. Right, so we can see here, 6 comes up twice. It has 2 different prime factors associated with it. Okay, in fact, the other numbers only have 1 because 4 is 2 times 2, 8 is 2 times 2 times 2, and 9 is 3 times 3, right? So when you prime factorize all of these other numbers, you only get 1 output value. Whereas with the number 6, it could either be 2 or it could be 3 because 6 is 2 times 3, okay? For the second one, number of days in each month. So this guy is a function. So this is yes, okay? And that's because each specific day in the range values that were given is only associated with 1 value, okay? If I had the number 29 in here, how would that change? Yeah.
February.
Yeah. If 29 was in here, February would actually be associated with 2 output values. It would either be 28 days or 29 days, okay? However, that is not part of the range. And so given the range that we have, it's only associated with 1 output, okay? Do you guys know that actually, you know how a year is 365 days? Okay, so that's the length of time it takes for the Earth to orbit the sun. That's actually not accurate. It actually takes 365 and a quarter days. And that's why we have leap years. Every 4 years we catch up. So that, because if we didn't, over the course of like 100 years, the seasons would be all off, right? Okay, that's just a little tidbit. All right, now we haven't talked about graphs. When you have the representation of a graph, when that is the representation of your relation, you can do something called a vertical line test. And what that is we take a vertical line, because remember the input values or the domain values are on the horizontal, and the range values are on the vertical. And we sweep it across the graph. And if that vertical line intersects the graph, or if the graph rather intersects the vertical line more than once, it is not a function. Because, for example, here,
Ashley Campbell, please come to guidance. Ashley Campbell.
and here, it intersects either 2 or 3 times. That means for the input value of 8.5, there are 2 heights associated with this. This one specifically looks at your height versus your shoe size. Okay? You guys okay? Yeah? Okay. For a shoe size of 9, there are 3 heights associated with that shoe size. Okay? So this is not a function. Okay? This guy, as we sweep the vertical line across, does it ever intersect the graph more than once? No. That means every input only has 1 output. If it intersects only once, there's only 1 output associated with that input. So this is a function, yes. Okay, and graphically, a lot of people find this one really easy, right? Because you can just sweep the line across, look for the number of intersections. Okay? You don't always have a graph, though. All right, so you guys very, very, very quickly do this one. And then we will keep going.
If I could like run to the library and print it out. Okay, thank you.
Okay, so what do we think? First one, yes or no? Yes. Second one? No, right. There are lots of places. If you want justification, just show at least one spot where the line intersects more than once, right? This input of 160, this is looking at your mass versus your height. So if you're 160 centimeters, there are 2 different masses associated with that. Okay? All right, example 3. So here we have a table of values that compares the number of marbles and the mass of that number of marbles. Okay? So first question is, why is this relation also a function? Given this data set? Yes?
The number of marbles doesn't appear more than once.
Yeah, so the number of marbles doesn't appear more than once. For each unique number of marbles, there is only 1 mass, right? So that would be sort of the answer of number of marbles doesn't appear only once is satisfactory, but a better answer is to say there's only one mass associated with each unique number of marbles. Okay, because that really sort of gets at the crux of the definition of function. There's only one mass associated with each unique number of marbles. Okay. Identify the independent variable and the dependent variable and justify your choices. Okay, so what is the independent variable here? Yeah. Number of marbles. Dependent is mass. Why is that? Yeah.
Because without the number of marbles, there would be no, without the marbles, there would be no mass.
Yeah, that's a good way of putting it. Without the marbles, there would be no mass. Totally, right? And typically, I also think back to science as well. If you were doing an experiment, would you set the mass value and then be like, how many marbles does this go with? Or would you set the number of marble values and then take the measurement of the mass, okay? Whatever you are setting, that's independent, okay? Yeah, so I liked both those answers. I like that. Actually, I've never expressed it that way or heard that before. That's quite nice. Without the number of marbles, or without marbles, there would be no mass. The other really sort of simple answer is just the way the table of values is set up, right? Independent is always on the left. Dependent is always on the right, okay? So here we are asked for justification. So you need to go a little bit further, but if you're just asked to identify what's independent and what's dependent, look for that, okay? So you could also say the mass or the total mass depends on the number of marbles on the scale. Okay, so there's lots of different ways that you could express that. Okay, what is the domain and range? So we've done this a lot, so let's just go through this really quickly. The domain is the input values or the independent values, so those are numbers 1 through 6. And then the range are the mass values, so that is multiples of 1.27. All right, 1.27. 2.54, and here it looks like the marbles are identical, right? Because every time we increase the number of marbles by 1, the mass increases by 1.27. .62. Okay, so there is our range. Here's another example. Oh no, that's it. I thought there was one for you to try. We're going to do 2 lessons in one day today because they are very, very similar. They kind of are on the same topic and they're both really short. So we're also going to talk about function notation. Okay? First part of today's class was on what is a function? What's the definition? How do we tell if a relation is also a function? Next, we are going to talk about how do we specifically when we have an equation, actually, communicate that something is a function. And the way that we do so is using something called function notation, okay? So let's just look at a normal sort of equation that we might have. We might have something like y equals negative 4x plus 6. I think that's the one that we looked at from last class at the very beginning, okay? This is something that does not use function notation. We have these 2 variables, x and y. Y is equal to negative 4x plus 6. Okay? If we were to convert this into function notation, it would look like this. f of x equals negative 4x. Okay? The y becomes something called f of x, or you could use another letter for f. You could use g of x, h of x, t of x, y of x if you want. But essentially what this shows is that this is a function, we're using f for the word function, that is dependent on this variable x. F is a function of x, or f is dependent on x.
We're doing retakes today, so we're just going to call down grades at a time, actually. I'm looking at grade 10 students with last names A through M. If you could make your way to room 235 for retakes, that's any grade 10 student with last name A through M in room 235.
All right. So it seems like we're going to have a couple interruptions today. That's all good. If you need to leave, just go and come back. So how do we deal with this? Essentially, the y is just replaced with f of x, okay? Now, what goes in here? In here goes, where the x is on the left side, whatever x value we want to plug in here, okay? So for example, if I wanted to find f of 1, what that means is I'm going to replace the x on the left, or on the right, with the value 1. Okay, so this is going to be negative 4 times 1 plus 6, and that is 2. Okay, so we would say f of 1 equals 2. 1 is the input value, 2 is the output value. Okay, you can kind of think of this equation as like a little function machine. So we are going to put in the value 1. It's going to perform or apply a rule to that 1. And the rule is multiply the 1 by negative 4 and then add 6. And then it's going to spit out the output value of 2. Okay? If I said, for example, let's try another one. Find f of 7. Okay, if you want to find f of 7, you're going to essentially replace the x on the right with whatever this number is. So it will be negative 4 times 7 plus 6. Okay, and that is what? Negative 28 plus 6, negative 22. Okay, that's really all that we do when we are looking at function notation. Now you can also be asked something like this. Determine x if f of x equals, let's say, negative 6. Okay. Now, we don't know what the x value is, so we can't plug in anything for x, but we know what f of x is. If you look at this equation, we know what the left side of the equation is. F of x equals negative 6. So how do we deal with this? We replace the f of x with this value. F of x equals negative 6, so that's what we get to sub in. We sub in on the left. Okay, so negative 6 equals negative 4x plus 6. Now we actually have to do some algebra to solve, right? We need to maybe subtract 6 from both sides. And I'm running out of room here, but I'm going to get negative 6 minus 6 is negative 12 equals negative 4x. And then we can divide by negative 4. Okay, and we end up with 3 equals x. Okay, so what does that mean? F of 3 equals negative 6. If you were to put that in as a coordinate point, you would have the point 3, negative 6. Okay, essentially, if you have a number over here in this set of brackets, you know the x value, and you need to plug it into the equation. If you know the f of x value, then you don't know x, but you know what the y value is. And so you plug in on the left. And you have to solve. Okay? And I know this seems like we're complicating things, but as I said earlier, as you get into higher levels of math, you'll sort of come to appreciate a little bit more why we use this. And really, it shows a dependency. It almost sort of reduces the relation to one variable. Because what we're saying is, to get this output value, we have to apply some rule, and the rule is dictated by this equation, but it all depends on what the x value is. Okay? All right, so let's go through some examples. If f of x equals 2x minus 1, find f of 2, and find f of x equals 2. Okay, so if you know this number in here, you sub in for x on the right. Okay, so we're essentially going to go f of 2 equals 2 times 2 minus 1. And that's 4 minus 1, which is 3. Okay, when you have f of x equals 2, we don't know what the x value is, which is on the right. But we know what f of x is on the left. So here we're going to sub the 2 in on the left. 2 equals 2x minus 1, and then we can solve. Okay, so we can like add 1 to both sides, and you get 3 equals 2x, divide both sides by 2, and you end up with 3 over 2, or 1.5 equals x. Okay, so x equals 1.5, or 3 over 2. Okay, so that would correspond to the coordinate point 1.5, 2. And essentially, sometimes people find this helpful. I'm going to put this down here maybe. When you were asked to determine f of a number, and there's a number in there, that is when you're going to sub the number for x on the right. Okay? If you were asked to determine f of x equals a number, then you sub the number in for f of x on the left and solve for x. Okay, so I want you guys to try, oh no, there's a couple more that we were going to do. Okay, so let's just do these two really quickly, and then I'm going to get you guys to try these two. Okay, one thing that I want, well, no, I'll mention this after we do these two. Okay, so here's a new function. Now f of x equals negative 3x plus 5, and we're asked to find f of x equals negative 4. So which side of the equation are we going to sub that negative 4 into? Yeah?
The left.
The left. We're going to sub negative 4 in for f of x. So we are going to have negative 4 equals negative 3x plus 5. And we have to solve now, right? So subtract 5 from both sides, and we get negative 9 equals negative 3x. Divide by negative 3, so we're solving like a linear equation here, and we get that x equals 3. Okay, what if we're asked to find f of negative 4? Then what do we do? Where do we sub this negative 4? Yeah.
The right.
The right, so we sub in for x on the right. So f of negative 4 equals negative 3 times negative 4 plus 5. And that's 12 plus 5 is 17. Okay? So what I was going to say before, and then I stopped myself, is f of x is typically, so the letter f is typically you'll see this a lot, the letter that we use for function notation, I think because of the word function, right? But it doesn't have to be that way. And particularly when you're looking at more than one function at a time, oftentimes we use different letters to distinguish one from another. So you can also see g of x, h of x, r of x, whatever letter you want. You wouldn't see x of x, it would have to be a different letter, but you could see a different letter. You can see in this example here, we don't even have an x in here, we have d of t. I'm guessing this function is relating distance to time. And we're saying your distance depends on your time, how long you've been going for, right? So if you're driving a car, if you're going for a run, how far you've gone depends on how long you've been going for. Okay, so I want you guys to try these ones. I'll comment. Do you have a question that?
Yes, it pertains to this.
Yep.
Scroll down, please, because I didn't finish the notes. Or
Okay.
scroll up, rather. Like
Go down.
yeah, go down.
Oh, here.
But,
I see.
yeah,
Yep. Okay, so I want you guys to try those two function notation questions. And then we will do another application question. How the variables interact, okay? So the equation v equals negative 0.08d plus 50 represents the volume, v liters of gas, remaining in a vehicle's tank after traveling d kilometers, okay? So you can think about this. I don't know if any of you guys have, how many people have their learner's license? Anyone? A couple of you? Have you had the joy of filling up the gas tank yet? No? Yes? I have to tell you, I was scared of filling up a gas tank when I got my driver's license. And back then, there were full-service gas stations. And I felt like I didn't know how to do it. So I ended up just going to the full-service gas stations and spending more money on gas. And then I figured it out. I think what happened was, suddenly it was all the self-service gas stations. There weren't any gas attendants anymore. So I was like, well, I better figure out how to do this. All right, so you fill up your gas tank. As you drive more and more and more, what happens to the gas tank? Yeah, it empties, exactly, right? So when the gas tank is full, some of you might know how to reset the trip. What's it called? The tripometer or whatever. Tells you how far you've gone, you can reset it. And I personally always, when I fill up my gas tank, reset that to 0. So I can see this is how many kilometers my car is going on a full tank of gas, right? Because when you empty it, you can see how far you've gone. Okay, so essentially what's happening is when you've gone 0 kilometers, you're gonna have a full tank of gas. As you travel more and more and more and more and more, your gas tank is emptying, okay? So this would kind of be a description of the function, right? Now, how much do you think, let's say you go 1 kilometer. How much do you think the gas tank empties in 1 kilometer? Yeah. Okay, very little. So I'm looking at this particular relation. Okay, I'm going to look at A. So let's actually write this in function notation first, because that's a really simple thing to do. If you have V equals negative 0.08D plus 50, all you need to do to write it in function notation is go V of D equals negative 0.08D plus 50. That's all you need to do. Replace V with V of D. Volume is dependent on the distance that you've traveled. Okay, now, describing the function. So, I'm going to tell you a little trick. If you don't know what the function's about and you can't use any specifics in describing the function, we've kind of described a bit about what's going on. What you start with a full tank of gas. As you travel more and more and more, the gas tank empties. Okay? One thing you can do to get a really clear picture of what's going on, to describe it is determine V of 0 and V of D equals 0. These are the extremes. So this tells us what is the volume when you've gone 0 kilometers. What does that actually tell you about the situation, about your car? Yeah.
How much gas do you start with?
Yeah, how much gas you start with, the capacity of your gas tank. Okay, what does this tell you? V of D equals 0. So now this piece, the volume equals 0, and you're looking for D. What does that tell you? Yeah. How far you can travel on a full tank of gas, on one tank of gas. Exactly. This is very informative. Okay, so if you're not sure, and by the way, as we go through this unit, and particularly linear functions, you'll probably get a better sense of this, but you can use these sort of extreme values to figure out what's going on. Okay, so for V of 0, that's going to be negative 0.08 times 0 plus 50. What is that? Yep. Yes, 50. So what does this mean? When you've gone 0 kilometers, you have 50 liters in your tank. This is the capacity of your gas tank. Okay? If you want to figure out this, V of D equals 0, then you're going to plug a 0 in on the left side. 0 equals negative 0.08 D plus 50. So when the volume of 0, how far have you gone? Okay, so to solve this, we can like maybe subtract 50 from both sides. Right, so this cancels 50 plus, or 50 minus 50 is 0. And we have negative 50 equals negative 0.08 D. Divide by negative 0.08. Okay, and that, I don't know what that is. What is that? You need a calculator. Negative 50 divided by 625. Okay, so this is the, I don't have room to write this. This is the distance that you can go on a full tank, or on one tank of gas, rather. Okay, it's a good thing to know this about your car, because you kind of, if you're planning a trip, a long road trip, you want to think on the map, like, where am I going to have an opportunity to fill up, right? And take other things into account as well, like, for example, highway driving. You can go a lot further using 1 liter of gas than city driving. So there's, you know, there's more than one factor, but it's a good thing to know. Okay, so what does this all mean? Okay, well, does anyone want to take a stab at putting this into words about what is going on between the two variables in this relation, in this function? How can we describe it? Yeah.
The distance you travel is dependent on the volume of gas in your tank.
Not quite. Almost. The distance you travel is dependent on the volume of gas in your tank. Which do we think is the dependent and independent variable? Yeah.
The distance is the dependent.
Distance is not dependent. So V of D is like the Y. Okay, D is like the X. Okay, so volume of gas in your tank depends on how far you've gone. Does that make sense? The distance you've traveled does not necessarily depend on the volume of gas in your tank. Okay, it might seem like that, because there's a correlation between the two. You could like take a jerry can and take some gas out, and then you have less tank in your gas, that sort of thing. Okay, so yes, the distance, the volume of gas in your tank depends on how far you've gone. Okay, the capacity of the tank is 50 liters, and as you go further and further and further, the volume decreases. That would be like a full description. I'm actually running out of space here, so I am going to write this down here. So the volume of gas in the tank depends on, right? So think F is a function of X, or F is dependent on X. Volume is a function of distance, or volume is dependent on distance. Depends on the distance the car has traveled. Okay, the fuel tank capacity is 50 liters, and as you drive further, the amount of fuel in the car decreases. Okay, that would sort of be a real full explanation of what's going on here. Okay, for B, we are asked to determine V of 600 and describe it, right? So for B, what is V of 600, and can we describe what's going on there in words? Okay, well, we have this function V of D equals negative 0.08D plus 50. If we want to know V of 600, what are we going to do? Yeah.
Sub in 600 up to 0.0.
Exactly. Sub in for D, 600. And then evaluate that, right? So negative 0.08, I'm just doing this on a calculator. Times 600 plus 50. So that is 2. What does that mean? If I were to translate this into a sentence that relates back to the variables in the problem. Yeah,
If you travel 600 kilometers, you'll have 2 liters of gas left in your car.
precisely. If you travel 600 kilometers, there will be 2 liters of gas left in your tank. Okay. So that is a description of what's going on between those two variables. Okay. I often will see people when I ask this kind of question say, when D is 600, V equals 2. Or they'll actually write in words, V of 600 equals 2. Okay. That's not actually a description of what's going on. If you have a context and you're asked to describe, you have to make a connection to the actual variables and what they represent. Okay. All right. C. So here we are asked, what are we asked? Determine the value of D when V of D equals 26, and what does this represent? So here we have V of D equals 26. We want to know what's the value of D. What are we going to do to figure that out? What should we do first? Yeah.
You replace V of D with
Yeah, so you replace the left side, the v of d, with 26, and you write out the rest. And then we have to solve. Okay, so first that involves, oh, d, sorry, I forgot the d in there, that's pretty important. First that involves isolating the d term, which means we have to undo addition of 50, so we're going to subtract 50 from both sides. Okay, so 26 minus 50 is negative 24 equals negative 0.08d. And then how do we solve for d at this point? Yeah.
When you divide negative 0.08 by negative 0.08.
Yes, or you divide negative 0.08d
Or, yeah,
by negative
by
0.08.
do the same thing with the
Yeah, okay.
It
These
isolates the d.
These cancel because anything divided by itself is 1. So this part makes 1. And on the left, left. Is that 300? I think is it 300? Yeah, okay. Okay, so how can we put this into words? What's a description of what's going on here? Essentially, we have v of d equals 26. And we found out that d is 300. So if we were to actually kind of put this into a point, we could write v of 300, because that's what d equals 26. You could, as a coordinate point, have the points 300, 26. What does that mean? The d value is 300. The v of d value is 26. You may actually want to look at the first description that we came up with, because when we're describing, we want to connect back to the actual variables and their meanings. Yeah. Yeah, if there's 26 liters of gas in your tank, then you have gone 300 kilometers. The car, has traveled 300 kilometers, exactly. Okay, questions with that so far? All right, so the last thing that I want you guys to do is this one. The equation C equals 25n plus 1,000 represents the cost, C dollars, for a feast following an Arctic sports competition, where n is the number of people attending. Okay, so you've got, you're planning like some sort of party or gala, and this is around a sports competition. Some of you guys may have been to this sort of thing if you're on a sports team, and there's a big party at the end, or you could even think it's similar to like a wedding or something like that. And the cost of putting on an event depends on how many people are there, right? So this is essentially what's going on here, right? So cost C dollars for a feast following an Arctic sports competition, where n is the number of people attending. Okay, so I want you to describe the function and write the equation in function notation. Okay, when you're describing it, try and use as many details as you can. And sometimes it's easiest to, in particular, find this guy, v of 0. That's going to actually tell you something about the situation. Okay? I'm going to stop the recording now because that's all we're going to do for today. But I want you guys to finish this question and I'll just come around and see how you're doing.